Alright, starting back where we left off, we're looking at a strong base solution, and so we're going to have the base breaking apart in water. Whenever you have a strong base, you don't include water in the reaction because you're just going to dissociate that strong base to give you some more hydroxide in solution. So if you have a strong base, single arrow, and we know that at the end we're not going to have any of that strong base left because it's all dissociating. So 5 times 10 to the negative 2 would be your initial, 0 for these two, minus x. So we now can see that if 5 times 10 to the negative 2 minus x is 0, then x must be 5 times 10 to the negative 2. Right, so that is our OH. If we're trying to find the pH, how would we do that from the OH value? Well, we would first find the pOH, which is the negative log of the OH concentration. And then from there, we can find the pH. So plug in those numbers into your calculator and be sure you can come up with this pH. So on strong acids and strong bases, we're going to completely dissociate. Our E line will be 0. If we're doing weak acids, however, we're going to have an equilibrium situation. So our E line is not going to be 0, and we're going to use our K value to solve. So in the next example, we're looking at a weak acid, and we're looking at acetic acid. Here in this first example, we have a solution that is 1 times 10 to the negative 4th molarity, and then we have a K value of 1.8 times 10 to the negative 5th. That 1 times 10 to the negative 4th molarity is our initial concentration, and then we have our K value. Now notice that those values do not differ by very much in terms of the exponent on the 10. So because they're so close together, you would need to use the quadratic equation for this. However, on the AP exam, you never have to use the quadratic, and so we're just going to switch to the next problem. Okay, so we're going to skip over this one and look at the next one. In this next problem, okay, down here, we want to calculate the pH of a 0.1 molar solution, and the acetic acid Ka value hasn't changed. So now 0.1 and that times 10 to the negative 5th, those are different enough that we can say that x can be negated, and so we won't have to use the quadratic. So we're going to solve this one. So we have our initial, our change, and our equilibrium given. They already set up the Rice table for us. They wrote out the Ka expression over here, and then we're just going to plug everything in. So we have 1.8 times 10 to the negative 5th equals our products, x squared over our reactants, .1 minus x. Right? In this case, we can, let's zoom in a little bit here, we can negate this x because the initial value and the K value are different by a factor of more than 100, or 10 to the second. Then I can solve for x. So I'm going to cross multiply, and that'll give me 1.8 times 10 to the negative 6th, which you see right here. And then I can square root that. So when I square root that, I got 1.34 times 10 to the negative 3rd. That is my x. Okay, now we talked about how you can negate x if it is added or subtracted, and I want to explain why. If x is going to be really small, which it is pretty small here, 1.34 times 10 to the negative 3rd, then adding or subtracting that from a number is not really going to change the number's value very much. For example, if we do 0.10 minus x, which is 0.00134, we will get 0.099. Okay, so we really didn't change the value very much by adding or subtracting x. And that is why, as long as K and your initial value are different enough, you can negate that x because it's not significant when it's added or subtracted. It's only significant when it's multiplied or divided. So that's the explanation there. So going back to our x value, which we found to be 1.34 times 10 to the negative third, if I'm looking for the pH, what do I do to that x value? Take the negative log. So 1.34 e to the negative 3, then I'm going to hit the log button, and it tells me that the pH is 2.87. In the paragraphs below, it explains some more why we can negate x, and it also works this using the quadratic to show you that you get pretty much the same answer. So we can negate x, and that's a really good approximation. Right, at the beginning of the next slide, it has steps for solving weak acid problems. These are really good to read over if you want to pause and read through them. In summary, I would say when we have weak acid or base problems, we want to do a Rice table. We want to use our Ka or Kb expression to solve for x. And then from x, we can do the negative log to find our pH or our pOH. So here we have an example of a weak acid problem with hypochlorite, HOCl. So the first thing we're going to do, as I said above, is a Rice table. So HOCl goes to H plus and OCl minus. We have a 0.1 molar solution, so 0.1, 0, 0. Now I left out water. If you include water, then you would have H3O plus. Minus x, plus x, plus x, 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 0.1 minus x. So Rice table, then your K value, 3.5 times 10 to the negative 8, that's our K, is equal to our products, x times x, no coefficient, so x squared, over 0.1 minus x. This is a really small K value, so I can negate this x, or excuse me, negate that x because added or subtracted, and then solve for x, will be my next step. Once you get x, how do you find the pH? Well, x is H plus, so I can just take the negative log of x to find my pH. So finish out that problem and check to make sure you get the right pH there. On the top of the next page, we have a really important note about a mixture of acids. So if you have two acids in the same container, which they'll do to kind of try to throw us and try to make the problem seem more complex than it is, but if we have two acids in a container, only the stronger acid is going to contribute to the pH in a significant way. So really, only the largest Ka value acid is the one that you have to worry about. So what do you do if you have a mixture of strong acid or a mixture of two acids? Determine the pH based on the stronger acid and ignore any others. So if you have a strong acid and a weak acid, you just use the pH from the strong acid. If you have a mixture of two weak acids, then you look at their Ka values. The one with the larger Ka is the one that we're going to use to determine the pH. So in exercise 12, we have a mixture of HCN and HNO2. Which of those two is going to contribute the most to our pH? Well, that's going to be the HNO2 because its Ka value is much larger than the Ka value of 10 to the negative 10 from HCN. So to solve this problem, I'm only going to use my HNO2. Going to use a Rice table. I am going to solve for x using Ka, and then I'm going to take the negative log to find the pH. So work through that one and make sure that you can get the correct value for the pH. We'll come back together and do the cyanide concentration. That's a second question. We'll do that one in class together. So y'all remind me, put a star there or something to remind me that we're doing this part together. Exercise 13 is talking about percent dissociation. So first, what is percent dissociation? That is the percentage of the compound that has broken apart. Okay, what percentage of the compound dissociated or broke apart? So to find that, you would take your X value, that's your change, that's how much broke apart, and divide that by your initial value, and then multiply by 100. So we'll do A together, and then I want you to try B on your own. So for A, we've got HC2H3O2. We know that's a weak acid. A strong acid would have 100% dissociation, but on a weak acid, we're going to have a very small percentage. So that's what we're trying to figure out. I'm not including water, but you're welcome to do so. All right, I have an initial value of 1, 0, 0, minus x, plus x, plus x, 1 minus x, x, and x squared over 1. I'm negating that x that's being added or subtracted is equal to 1.8 times 10 to the negative 5. All right, I get an x value of 1.8 times 10 to the negative 5th square rooted. So x equals 4.24 times 10 to the negative 3rd. That's my x value. So to find percent dissociation, I would do x, 4.24, times 10 to the negative 3rd, over my initial value, which was 1, times 100. And that's where the 0.42% comes from. So only 0.42, not even 4.2, 0.42% of this broke apart in water. So that's why we call those weak acids. A very small percentage of them is breaking apart. On B, I want you to do the same thing. You have a different starting amount, so you'll have a different value on the bottom when you calculate percent dissociation. Your rice table will be set up pretty similarly. So find x, divide by your initial, and see if you can come up with 1.3%. Exercise 14 is very similar, but instead of giving us the Ka and asking us for the percent, they give us the percentage and they ask us to find the Ka. Right, so here we go, diving in again. Always a rice table to start a weak acid problem. Double arrow, H plus, C3H5O3 minus, 0.1 molarity, 0, 0, minus x, 0.1 minus x, and x. Now, I can now say x squared over 0.1 equals Ka, but I don't know the Ka value. But I have this key piece of information, that 3.7% dissociated. So 3.7% broke apart. So 3.7% is my x. So I'll go 0.037. 0.037 is 3.7% times 0.1, my initial value, equals. So x equals 0.0037. 3.7% of my initial. So then I can say, okay, x squared, 0.0037 squared over 0.1 minus 0.0037 equals Ka. Right? Here, this value, this 0.0037 is really small compared to 0.1, so you're going to get like 0.9 something, so it doesn't really change the 0.1. So you could leave that off if you wanted to, and you would get still pretty close to this answer. Right? So you can plug that in and make sure you can come up with the correct Ka value. That is how you find Ka if you know the percent dissociation. Right? What if we have a weak base? We're going to work weak base problems the same way we work weak acid problems. So let's write down the steps we said. We're going to use a rice table. We're then going to use, not Ka this time, we're going to use Kb to find x. The only difference is X is your OH. So then we've got to find POH, and then we can find pH. All right, so let's start. We have a weak acid, NH3, a weak base, NH3. What do bases do? Bases accept a proton or a hydrogen. Where's it going to get it from? It's got to get it from water. So NH3 plus H2O, double arrow, NH4 plus OH minus. This water is a liquid, pure liquid, so no effect here. 15 for my initial, that's a huge value for the initial. 0, 0, minus X, plus X, plus X, 15 minus X, X. Are you noticing a trend here? Every time we have a weak acid or a weak base problem, we always end up with X squared over the initial. We negate that added or subtracted, equals our K value. All right, from here we'll solve for X. Once we get X, we'll take the negative log of it, but that's going to be the POH. And then from there you can find the pH. Okay, so pause, finish solving that, and make sure you come up with 12.2. All right, I want you to try exercise 16 on your own. The answer is given there in the corner, 12.32. Make sure you can come up with that. Methylamine, you say, what the crap, Miss Waters, is methylamine? Well, it doesn't even matter. What you can do is you can just call this B, because you know it's a base. So to write our reaction, we can say B plus water is going to give us what? What do bases do? They pick up a hydrogen. So HB plus and OH minus. Leave off the water. You'll put your initial values, put your X's, solve for X using your KB. X is your OH, so you find your POH, and then you find your pH. All right, the next section is talking about polyprotic acids. So we said earlier, I think in video 1, that polyprotic acids are acids with more than one hydrogen that can be lost. This will happen in steps, and each step has its own Ka value. The first dissociation, or losing the first hydrogen, will be the greatest, and the rest of them will have much smaller equilibrium constants. So after each hydrogen is removed, the acid gets weaker and weaker, and that's why there's a smaller Ka. The reason for this is because as you lose a hydrogen, you have a negative charge, and that negative charge is going to make it harder to remove a positive proton. So we have an example here of H3PO4, and we have its Ka value. If you'll look down at the chart, this is the first acid listed here, phosphoric acid, and losing the first hydrogen gives us a Ka value of 7.5 times 10 to the negative 3. When we lose the second one, we call that Ka2, and that has a value of 6.8 times 10 to the negative 8. And then if we need to lose a third one, notice how small that value is. 4.8 times 10 to the negative 13th. That's 0.00000, 12 zeros, 48. Such a small value compared to the Ka for H3PO4, the first one, which was much larger. So if we think about this in terms of whether it's reactant or product favored, the first reaction is reactant favored because K is less than 1. So I would have more reactants than products. I would make some products, okay, but not a lot. Once I make those products, that H2PO4, it can then go and be the reactant in the next step. But I don't have much of it. I do have some. Some of that, a tiny amount, will break down into HPO4. And then some of that, a tiny amount, will break down into PO4. So if they ask me to list these in order of their concentration, the H3PO4 is going to have the highest concentration because it's a weak acid, so just a little of it breaks apart to make some H2PO4. And then a tiny bit of that breaks apart into HPO4 negative 2, and then a tiny, tiny, tiny bit of that breaks apart into PO4 negative 3. So I have very little PO4 negative 3 in the end, and I still have quite a bit of H3PO4. But that would be the order of their concentration. So some H3PO4 breaks apart to make a little H2PO4, a little of that breaks apart, and then a little of that breaks apart. Okay? So you can think of if you had a sample and you broke off like one piece of it, that would be your H2PO4. And then you broke that into pieces and broke off one of them, that would be your HPO4. And then you broke that into pieces, and that would be your PO4. Okay, so it's like sharing and then sharing and then sharing again. That person at the end that you're sharing with, they're going to get the least amount. So in exercise 17, when it says calculate the pH of a 5 molar solution of H3PO4, well, H3PO4 can give off 3 hydrogens, but it's only the loss of the first one that really affects the pH. It's the same thing that we were looking at when we mixed acids. You only use the one with the higher Ka value. Same thing here. If you have a polyprotic acid, you will write it only as losing that first hydrogen. We have a 5 molar, so of course we know now it's going to be 5 minus x on our E line, and x, okay, x squared over 5.0 minus x. And then if we look back at that chart, you'll see there are 3 Ka values for H3PO4. So which one do you use? You use the largest one, because that's the only one that's going to have any real effect on your pH. So once you plug in K from the chart, solve for X, take the negative log of it, and we should get this as our pH. All right, notice we're not going to calculate these concentrations like it asked us to do, but I wanted you to notice the extreme difference in these concentrations. So the H3PO4, which is your main acid, your strongest acid, some of it is going to break apart, but still not much because it's a weak acid still. So it still has the highest concentration. So you see here most of it, 4.8 out of 5, is still stuck together. Then some of that can break down into H2PO4. So you have less of that, 0.19. Then the next one, HPO4 negative 2, look how tiny. 10 to the negative 8th of that, and then 10 to the negative 19th of the PO4 negative 3. Okay, so I just wanted you to see the comparison there. Your first original acid, because it's weak, almost all of that sticks together, and then you have tiny amounts broken off from there. All right, we're going to see and 19. We're going to talk about salts. Okay, salts. Now, when you say salt, you're like, oh, sodium chloride. Okay, salt is just referring to an ionic compound. And a salt or an ionic compound can actually change the pH of water. Sodium chloride is what we call a neutral salt. It does not change the pH of water. So neutral salts are formed from the cation of a strong base and the anion of a strong acid. So for example, NaCl came from NaOH and HCl. NaOH is a strong base and HCl is a strong acid. So that's how we make NaCl salt, and that is called a neutral salt. A basic salt is going to increase the pH. Increase the pH. And it is formed from the cation of a strong base and the anion of a weak acid. For example, K2C2H3O2. So the K part came from KOH. That's a strong base. But the C2H3O2 came from H2C2H3O2, which is a weak acid. So if it comes from a strong base and a weak acid, then it is a basic salt. And when you mix that with water, it would make the pH go up. Now, how does it make the pH go up? If something is basic, it has to accept a hydrogen. So which part of this, if we look back at this formula right here, K2C2H3O2, which part of that could accept a hydrogen? Well, hydrogens are positive, so the negative anion is going to take a hydrogen from water, and that's how we get an increase in our pH. That's why it's a basic solution. If we have an acidic salt, that would be a salt from a weak base reacting with a strong acid. For example, NH4Cl. Well, the NH4 came from NH3, and the Cl came from HCl. So that's a weak base and a strong acid, so that salt would be acidic. Now, in order to be an acidic salt, what do acids do? They donate a hydrogen. So which part of this acid could donate a hydrogen? The NH4. So NH4 plus in water would donate a hydrogen to make NH3 again, its conjugate base, and that is why that is an acidic salt. This is a salt that could donate a hydrogen. If both the cation and the anion are from weak substances, for example, if we had NH4 2C2H3O2, well, that is from NH3, which is a weak base, and that is from H2C2H3O2, which is a weak acid. So if that happens, you would have to compare their Ka and Kb values. Okay, and that's if Ka is greater, it's acidic. If Kb is greater, it's basic. And if they are the same or really, really, really close together, then that's going to be a neutral salt. So salt problems are one of the hardest types of problems from acid and base. Okay, so we're going to talk about how to think through these types of problems. First of all, look at the salt and ask yourself, which acid and base reacted to form this salt? Then ask yourself, are these acids and bases strong or weak? Think about the fact that strong wins. So if it came from a strong acid and a weak base, then it's going to be acidic. Strong base, weak acid, going to be basic. So once you predict whether it's going to be basic or acidic, then you can start writing your reaction. If you predict it to be basic, you know that we've got to make some OH. And if you predict it to be acidic, you know we've got to make some H+. So that could be the start of your equilibrium. The thing that came from the strong is going to be a spectator. So we won't include that in our reaction. And then whatever else came from the weak is going to be the reactant along with water. It helps sometimes if we write water as HOH, because that reminds us that we can take off that hydrogen and leave OH, or take off that OH and leave hydrogen. Okay, for example, what is the pH of a solution of FeNO3? All right, where did this come from? So the Fe came from FeOH3, which is a base, and the NO3 came from HNO3, which is an acid. FeOH3, that's weak base and strong acid. So if we have a weak base and a strong acid that made this salt, then this salt must be acidic. So if it's acidic, then we know we've got to make H+. So I write that over here on my product side. And I know water is a reactant. So I write that over here. The strong part, so I said that the NO3 came from a strong acid. The strong part is a spectator. So I'm getting rid of that. And then I'm reacting my Fe+3 over here. So what is the Fe+3 going to do? Is it going to pick up a hydrogen from water? Well, no, because hydrogen is positively charged. So the Fe+3 is going to pick up the OH part of water, because that's negatively charged. And it's going to leave behind the H+. Now we would need to balance this. So if it picks up 3 OHs to balance with its +3, then I'll need a 3 in front of water and a 3 in front of H+, which is what you see down here. These are usually going to show up on multiple choice questions, and what they'll ask you is, do you think the pH is going to be greater than 7, less than 7, or equal to 7? So you'll ask yourself, what kind of acid and base did this salt come from? If it came from a strong acid and a weak base like this one did, then I can say for certain that the pH is less than 7. All right, so on these down here, we're going to do the same thing. We're going to predict whether the solution would be acidic, basic, or neutral, and then we're going to write an equation to prove that. So in A, we have Na, which would come from NaOH, and C2H3O2, which comes from HC2H3O2. So NaOH is a strong base, so I'm going to cross that out, while C2H3O2 is a weak acid. So if it's a strong base and a weak acid, I can say that the pH is going to be greater than 7, which is basic. I also know then that OH is going to be a product, and of course water is a reactant. The reason I crossed out the sodium is because it is from a strong base, so it's a spectator. So then I have C2H3O2 minus reacting with water. It has a negative charge. What's it going to do? It's want to pick up a hydrogen to make HC2H3O2 with no charge. Right? So I know that it's basic, and this reaction proves why. Because the anion is going to react with water to pick up a hydrogen and leave me with OH minus. So you try that for B and C. Okay? It's okay to stumble. Just try to figure out, where did it come from, what do I predict my pH to be, and then try to write the reaction. Okay, starting on exercise 21, we're going to try to calculate the pH of a salt solution. So we have NaF. Right, salt, NaF. Where did it come from? The Na came from NaOH, which I know is a strong base, and the F minus came from HF, which I know is a weak acid. So strong base, weak acid, pH greater than 7. But they want me to calculate exactly what it is. Okay, so I know that I'm going to need a rice table. I know I'm going to make OH minus because I know it's greater than 7 because I have a strong base. And I know I'm going to react with water. Now in NaF, the Na is from a strong base, so that's a spectator. So F minus is going to react with water to form OH. And what's the F going to do? It's going to pick up a hydrogen from water, form HF. Water is not going to be included in my rice table. I'm going to have 0.3 of this, 0, 0, minus X, plus X, plus X, 0.3 minus X, X, and X. Ta-da! X squared over 0.3 equals. Now, equals K, right? But K what? They gave me a Ka value for HF. But HF is a product. And this is a basic reaction. So I need the Kb value. Okay, if you'll remember back, I think it was on the first video, but Ka times Kb equals Kw. What's Kw? 1 times 10 to the negative 14th. So I can say my Kb value is equal to my Kw divided by my Ka. 7.2 times 10 to the negative 4th. So that means that Kb is equal to, I got 1.39 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 on my calculator. Okay, so whenever you're doing a salt problem, you're always going to have conjugates, and they're going to give you the wrong K value because they're giving you the K value for the product. So in order to find the correct K value, you're going to use Ka times Kb equals Kw on a salt problem. But then from here, you can cross multiply, square root to find x, and once you find x, you can find the POH because x is equal to your OH. And then from there, you can find pH, knowing that pH plus POH equals 14. Exercise 22 is very similar. We're not going to do 23. We're not going to cover the information that is on the next page. If you have that page, I may not have copied it. Okay, and the last thing that I want to do is to talk about how to solve each of these problems. So we're ignoring that. So if you just find some spare space or a blank sheet of paper, okay, I want to go over the key equations and how to solve these problems. So some key equations are that the pH equals the negative log of the H plus. The POH equals the negative log of the OH. The POH plus the pH is equal to 14. Okay, those are just some key basic equations. We also need to know that the H plus times the OH is equal to 1 times 10 to the negative 14th, and that value is Kw as long as we're at 25 degrees Celsius. Another thing we can do with Kw is say that Kw equals Ka times Kb, as long as these two are conjugates. All right, these equations that we just looked at, they are on your equation sheet, and so you may just want to look and make sure you can identify those there. Another key equation is the equation for H plus and OH minus. How do we find those if we know the pH? Well, H plus is equal to 10 to the negative pH, and OH is equal to 10 to the negative POH. Those are not on your equation sheet, I don't think. I think they expect you to know the inverse of log and how to do that. But if you want to write those down somewhere just to jog your memory, that would be a good idea. Okay, so those are the key equations that we have for this section so far. And now I want to talk about what are the steps for solving acid-base problems. Okay, so the first step is always a rice table, no matter what type of problem you're dealing with. If it is strong, then remember your E is going to equal 0. For the reactant. Okay. The next step after the rice table would be to use the K expression to find X. Now remember, if it's a salt problem, Ka times Kb equals Kw. You're going to have to use that to solve. All right, once you have X, you're going to do the negative log of X to find pH or POH. And then if necessary, you would do 10 minus one of those to find the other one. So if you found POH, you do 10 minus POH to find pH. Okay, and that's basically it. That's strong acid, strong base, weak acid, weak base, and salt problems. The only thing extra that we need to keep in mind is when they throw things at us like polyprotic acids. We're only going to lose one hydrogen to find the pH. The other losses of hydrogen are very small and very insignificant. If we have multiple acids, we're only going to use the strong one to find the pH. If we have salt problems, we're going to have to figure out which part of the salt is going to affect the pH. Okay, so those are some ways that they could kind of change things up on us. But this is our basic problem-solving method for acids and bases.